Okay, so now we're going to be discussing section 11.3, or energy in simple harmonic motion, or SHM. So with simple harmonic motion, the total mechanical energy is going to be constant. So in other words, the sum of the energy, both kinetic as well as potential, is going to be constant. At points of maximum displacement, in other words, where x is equal to a and Vx is equal to 0, all of the energy is going to be in the form of elastic potential energy. So the constant total mechanical energy could be expressed as E is equal to 1/2 K A squared, where A simply is taking the place of the X. If you were to graph this, and you've got your displacement down here on the x-axis, it goes out to a maximum of A, and goes to a minimum of minus A. The energy, if you were to plot it on the y-axis, the total energy is going to be constant. If you look at the extremes of motion, all of your energy is going to be potential energy. In other words, this blue line. All of it is going to be potential here and here. None of the energy is going to be kinetic here and here. Now, as the object moves from minus A to 0, you're going to see the potential energy change into kinetic. They actually become equal at some point. And then as it passes through the equilibrium point, all of that energy is going to be kinetic. So the kinetic energy, as you may remember, for the object is going to be equal to 1/2 mv in the velocity in the x direction squared. Potential energy is going to be the energy in the spring, 1/2 kx squared. So the equation for the conservation of mechanical energy is going to be the kinetic plus the potential, and that's going to be equal to a constant. So the total mechanical energy is also directly related to the amplitude of the motion, which we just saw in the previous graph. When the object reaches the point x is equal to a or minus a, the maximum displacement, it stops momentarily as it turns back around towards the equilibrium position. At that point, the energy is entirely potential energy. Because E is constant, the quantity is also equals E at any other point. Combining the expression, this is what we end up with. The units, of course, are going to be in joules. And the velocity, the v of x, as well as x, are going to be the speed and position of the object at any arbitrary time in the motion. As you have seen, the energy is going to move back and forth between kinetic and potential. As long as there is no friction, the energy is going to remain constant. If you go through and if you solve this particular equation for v sub x, you come up with plus or minus the square root of the ratio of k over m times the square root of a squared minus x squared. Obviously, the unit should be in meters per second. The plus or minus symbol refers to the fact that for any given position x, the velocity can be positive or negative depending on which way the object is moving. It moves with its maximum speed as x is equal to 0. So if you put in x 0 here for x, you can see why that would be the case. That's going to be the biggest number you'll generate here, because x is the only thing that's varying. This is set, that's set, and this is set. This is the only thing that varies. If you go in and you substitute in plus or minus a over 2, in other words, half the distance between equilibrium point and the maximum extension, you end up with a velocity that's plus or minus the square root of 3 over 4 times the square root of km times a. If you go through and if you set x equal to 0, then you find that your maximum velocity is the square root of k over m times a. And you can see this is a description of what's going on. When x is equal to 0, in other words, at the equilibrium point, all the energy is kinetic. As you move to either side, it starts to change into potential because you're either compressing or stretching the spring. You can see the velocity, depending on, of course, which way it's moving. And then when you get out to the maximum level here, everything is all potential energy. The velocity is no longer moving, therefore everything is just simply potential energy. If you combine all of those graphs into one here, you get the same thing as what we saw in the summary. There are some more problems there that you might want to work through. If you try to make x greater than a or less than minus a, then what happens is the potential energy is greater than E. And that means you'd have to have negative kinetic energy, which that's not a thing. So x can't be greater than a or less than minus a. Weird thing is that in quantum mechanics, it is possible in some circumstances for a particle to traverse regions where classically it would have negative kinetic energy. This is important in alpha decay of nuclei and in the tunneling electron microscope, but it plays no role in the mechanics of macroscopic objects. In other words, the objects that we see, kinetic energy can never be negative. So just bear that in mind.